During classical Greece, not much was known that we know today about atoms. Although that is true, a philosopher by the name of Democritus had a theory that you cannot divide something for eternity. Democritus called these smallest indivisible things atomos, which translates to indivisible. Even though his theory was proven, later, another philosopher who was well known, named Aristotle, thought differently, and was believed because of his popularity, even though he was wrong. He believed that matter is infinitely divisible, and if you cannot divide it, your knife is not sharp enough.
In 1803, John Dalton, an English schoolteacher, discovered the law of multiple proportions, which states that the ratio of masses that will combine with 1 gram of another element is always a simple whole number ratio. John Dalton also created the atomic theory, which states that matter is made of atoms. Atoms are indivisible and indestructible. Atoms of the same element are identical. Atoms of different elements are somehow unique. Atoms combine in simple whole number ratios, and he listed the elements in order from increasing masses. His atomic model is a circle.
In 1869, Dmitry Mendeleev, who attended the University of St. Petersburg, was credited with the creation of the first useful periodic table. He uses the law of octaves, which was created 4 years before that by John Newlands, and he predicted the discovery of 3 unknown elements. He called them eka-silicon, eka-aluminum, and eka-boron. Even though he reversed the order of several pairs, his was still the most used and most accurate that they had at that time.
J.J. Thomson, a professor at Cambridge University in 1897, improved the design to hold a better vacuum and invented the cathode ray tube. The cathode rays were deflected in electric and magnetic fields and were attracted to the positive side, meaning that they were negative particles. By studying the magnitude of deflection, Thomas found the charge-to-mass ratio of the particles that made up the cathode rays. This ratio was more than 1,000 times greater than that of a hydrogen ion. This resulted in 2 possibilities. 1, these particles had an incredibly large charge, and 2, these particles were much smaller than atoms. J.J. Thomson then concluded that he had discovered the electron and created the plum pudding model.
In 1910, Robert Millikan, who attended the University of Chicago, performed the oil drop experiment in order to determine the charge of a single electron. He dropped oil into a container while manipulating the electromagnetic field and firing X-rays. By doing this, he determined the charge of an electron and therefore found the mass as well.
In 1909, Ernest Rutherford, who attended the University of Manchester, did the gold foil experiment to test the plum pudding model. He used alpha radiation, which is positively charged and is quite large, and he shot it at a gold foil which was a few atoms thick, and his expected results, using Rutherford's model, the alpha particles would go right through and hit on the detector on the other side. But what actually happened is, most of them, as predicted, hit the detector straight across, but some of them were deflected or bound off into a different direction, which was quite odd. He concluded that instead of being a plum pudding with a bunch of positive mass around it, that there was a positive nucleus, and this nucleus was dense and large compared to the electrons that were unexplained and were just around the nucleus in this electron cloud. He developed a new atomic model, which is called the nuclear model.
Niels Bohr was able to develop the next atomic model from the theory from Albert Einstein that light was quantized. This model explained flame tests, atomic emission spectra, and helped understand the position of electrons. In turn, Bohr created the Bohr model, which put electrons in energy levels, which we will explain later. This is quantum number n, which represents the principal quantum number, and it can be all positive integers from 1 to 7 and represents the energy level of the electron. And it can only be 1 from 7 because we only have 118 elements and 7 happens to end there. This is quantum number L, which represents the shape of the orbital. This balloon represents the s orbital shape, which is a sphere, as you can tell, I guess. Now, the S has 2 electrons demonstrated by these 2 BBs. You can see it right there and right there. And this little guy right here is the atom, or the nucleus of the atom.
Okay, this is the nucleus of the atom, which has the protons and the neutrons, of course. And this represents the p orbital, which has these 2 lobes where the atom can be found on either side, on top of, or anything. That's the orientation of the orbital. So you can have 6 electrons in this whole entire thing, and that's it.
This is the orbital. Right here's the nucleus, and this is the orbital pattern, shaped like a clover. If you're in the z-axis, it would look like this. Up to 10 electrons can be found within this orbital 95% of the time. This represents the f orbital. All these are the orbital patterns. Inside, what you can see is the nucleus. Up to 14 electrons can be found within this orbital.
This is M subscript L, which represents the magnetic quantum number and describes the orientation of the orbital. It can be all integers from negative L to positive L. Here we have a sphere, which is the orbital of S. Any way you change it, it will always be a sphere. This way, this way, this way. It's still a sphere. Then we have this dumbbell, represents the p orbital and only has 3 orientations. Here, here, and here. This is M subscript S, which represents the spin quantum number. Now imagine that I'm the nucleus and this is the electron. And there's only 2 ways that this thing can spin. Around me, this way, or around me, this way. Graphs of the 4 orbitals, S, P, D, and F. S is only present through energy levels 1 through 7, circular orbital. We have the p orbital, which is only present through 2 to 7, dumbbell shape. The d orbital, which is only present through energy levels 3 to 7, as you see this little flowery shape. And then we have the f orbital, which is only present through 4 to 7, and it's this.
This is how the electrons fill into the orbitals. This is the energy level, these numbers, 1, 2, 3, 4, 5, 6, 7. We only went up to 7 because 7F would be the last element that we have known in the periodic table, which is UU octium 118. So basically it goes like this, you just like that. Now go down here and here. Yeah, it's pretty normal, but you'd expect that it would go 3D before it goes to 4S. But really 3D has more energy than 4S. And everything in the universe is, how I'm always told by my chemistry teacher, lazy. So it'll go into the lowest energy form, and right here 4S has less energy than 3D. And then if you keep going, it goes like this, it goes like this, from there, there, and so on and so forth. And when you get to 7F, we're out of elements.
I believe that the shape of the periodic table is completely random. However, it actually represents the number of electrons in each energy level. Right here, is the s orbital, represented by these two columns. We have the p orbital, represented by these 6 columns. Next, we have the d orbital, represented by these 10 columns. And then we have the f orbital, represented by these 14 columns.